What specific problem does your work aim to address with regard to the representations constructed by large language models during training, particularly in the context of OthelloGPT?
My work aims to address the problem of understanding how large language models, specifically OthelloGPT, construct their internal representations during training, particularly in relation to their ability to perform complex reasoning tasks. We investigate whether these models develop coherent and generalizable world models, or if their representations are incomplete and brittle, as evidenced by their inconsistent performance in tasks like compositional reasoning and long-term planning. By employing sparse autoencoders, SAEs, and linear probes, we analyze the features learned at each layer of OthelloGPT, revealing a hierarchical progression in the model's understanding of game dynamics, such as board shape and tile stability. Our findings indicate that while linear probes can classify features effectively, they fail to disentangle overlapping or compositional features, which SAEs can achieve, thus providing deeper insights into the model's learned representations. Ultimately, this research seeks to enhance the interpretability of LLMs and improve their reliability in downstream applications by elucidating the nature of their internal world models.
How does the proposed algorithm work? Please illustrate it step by step, specifically detailing how sparse autoencoders, SAEs, and linear probes are implemented in your analysis of the features learned in OthelloGPT.
The proposed algorithm employs both sparse autoencoders, SAEs, and linear probes to analyze the features learned by OthelloGPT. First, the SAEs are utilized to transform high-dimensional neural activations from the intermediate layers of OthelloGPT into sparse interpretable representations by minimizing reconstruction error, which allows for the identification of distinctive and disentangled features related to board states and moves. Specifically, the SAEs extract residual stream embeddings from each transformer block, focusing on features that classify tile states, empty, player's piece or opponent's piece, and ensuring robustness by averaging results across multiple random initialization seeds. In parallel, linear probes are trained across all layers of OthelloGPT to measure feature accessibility and predict attributes from the model's hidden states. Each linear probe acts as a classifier that maps the hidden states to specific semantic features, such as tile color, by minimizing cross-entropy loss. The results from both methods are then compared, revealing that while linear probes show increased accuracy across layers, they fail to disentangle overlapping or compositional features, which SAEs successfully achieve, providing deeper insights into the hierarchical progression of learned features in OthelloGPT.
Can you elaborate on a simple example that demonstrates the inner workings of your proposed algorithm? For instance, how would SAEs or linear probes reveal distinct board features in OthelloGPT?
A simple example demonstrating the inner workings of our proposed algorithm involves analyzing tile color in OthelloGPT using both sparse autoencoders, SAEs, and linear probes. For instance, when we apply SAEs to the model's hidden states, they effectively disentangle features related to board states, such as identifying corner and edge tiles as significant early on in the learning process. This is evidenced by the heat maps generated from SAEs, which show strong activations at these positions, indicating that the model captures the board's shape and positional importance. In contrast, linear probes, while they can classify individual tiles accurately, reveal more dispersed activations across the board without clear structural patterns, failing to capture the compositional relationships between features. Thus, SAEs provide a more nuanced understanding of how OthelloGPT learns and represents distinct board features, highlighting the evolving dynamics of gameplay as the model progresses through its layers.
What are the theoretical or practical benefits of using SAEs compared to linear probes in your analysis, and how do they enhance the interpretability of learned representations?
The theoretical benefits of using sparse autoencoders, SAEs, over linear probes in our analysis lie in their ability to disentangle learned features into sparse interpretable representations, which is crucial for understanding complex compositional attributes. Unlike linear probes, which primarily identify features that correlate with classification accuracy without revealing distinct or overlapping features. SAEs provide deeper insights into the hierarchical progression of features across layers. Practically, our experiments demonstrated that SAEs uncover more distinctive features related to board states and moves, particularly in the context of OthelloGPT, where they highlight clear structural patterns and dynamic changes in feature activations. This enhanced interpretability allows us to trace how different layers of the model capture various aspects of gameplay, such as positional importance and evolving dynamics, which are essential for strategic decision-making. Overall, SAEs facilitate a more nuanced understanding of the internal representations learned by the model, thereby improving the interpretability of its decision-making processes.
How did you validate the effectiveness of your method? Please clarify the datasets used, experimental design, and metrics applied in your analysis of OthelloGPT's features.
To validate the effectiveness of our method, we utilized the OthelloGPT model, trained on a synthetic dataset consisting of random Othello game transcripts. Our experimental design involved comparing sparse autoencoders, SAEs, and linear probes to analyze the learned features across the model's layers. We specifically extracted residual stream embeddings from intermediate layers for the SAE experiments and trained linear probes to predict tile states, empty player's piece or opponent's piece, across all layers. The metrics applied in our analysis included the area under the receiver operating characteristic curve, AUROC, to measure the discriminative power of features, with a threshold of OROC greater than 0. 7. Indicating strong classification ability. Additionally, we computed F1 scores and assessed feature activations to evaluate the robustness and consistency of the learned representations across multiple random initialization seeds, ensuring that our findings were not artifacts of specific training conditions.
What specific results did you achieve with your method, and how do they contribute to understanding the internal representations of OthelloGPT and its implications for LLMs in general?
Our analysis using sparse autoencoders, SAEs, and linear probes revealed distinct differences in how OthelloGPT learns internal representations across layers. Specifically, SAEs demonstrated a hierarchical progression in feature learning, capturing structural patterns such as board shape in early layers and dynamic aspects like tile flips in later layers, with significant activations concentrated in the central tiles during gameplay. In contrast, linear probes showed increased accuracy across layers, but failed to disentangle compositional features, resulting in dispersed activations without clear structural patterns. This layer-specific learning suggests that different depths of the model are dedicated to distinct concepts, enhancing our understanding of how LLMs construct their world models. Overall, these findings highlight the importance of using interpretability methods like SAEs to uncover meaningful features, which can inform the development of more reliable and coherent LLMs capable of complex reasoning and long-term planning.